Hey, thank you very much for inviting me to talk. As Carl has said, I'm going to be focusing all about how do you get high quality data for data reuse and machine learning. PDB has been around a long time, and I'm going to tell you a little bit about that, and then how the data are actually treated so that it gave extremely reliable results that enabled protein structure prediction. So PDB, in that sense, is an exemplar. We know for sure that it worked. It provided the data that allowed an important piece of research to be done. The PDB Protein Data Bank is a repository for the three-dimensional structures of biological molecules. It started a very long time ago, basically while I was in my postdoc era. And the reason it started was that there were new protein structures being finished and published, myoglobin and hemoglobin being the first examples coming from England. And there were a bunch of young people, I used to be young, and we felt that there needed to be a place to put these data. Now remember, in those days, this was in the 60s, the data were on punch cards, maybe sometimes magnetic tape. Most of the data at that time was residing in Europe. So how do you actually get the data around? There was actually, as part of this, DARPANET allowed there to be some kind of pushing of data around, but most people didn't know anything about that. For whatever reasons, we did. So we did do some experiments, which I'm not going to tell you about at this talk. But at any rate, there was a lot of community activism to get a protein data bank started. And in 1971, there was a meeting in Cold Spring Harbor, and I show you at the upper right, there was a scientist from Brookhaven named Walter Hamilton, and he was very interested in biology. He was a chemical crystallographer, but quite well known at the time. He was young, he was in his early 40s, but pretty much a towering figure in the field. It's a picture of him talking to one of the people who did the structure of a protein named ribonuclease. His name was Hal Wyckoff, and there was this meeting in Cold Spring Harbor where everybody got together to learn about amazing new science. And I think we talked about perhaps 15 or 20 structures during that meeting, but everybody was riveted because it was such an exciting new field. At the bar, at the end of one of the days, this rowdy group of young people, including myself, went to Walter and said, "We need a protein data bank." I don't know why we went to him, but we did. And he said, "Okay, done." And so it'll be at Brookhaven. And so he flew to England and he talked to people from the Cambridge Crystallographic Database because he knew that it had to be global. They agreed there would be a collaboration. I then became a research collaborator at Brookhaven, and together with Edgar Meyer, who was a person who was very active in protein visualization and computational work, and we basically created the PDB just like that. And it went along. It did okay. People liked it, but it wasn't the big deal because there weren't that many structures and not very many people cared about it. However, in the 80s with the AIDS epidemic, the NIH said, they weren't supposed to say this to us, but they basically said, it was Marvin Kassman from NIGMS, he said, if we're going to fund structural biology that is going to be important for public health matter. These data must be public, and they must be, people must put the data in a database, because there were no rules at that time that it had to be anywhere. So a bunch of committees were set up to figure out what the guidelines would be, what kind of data we're talking about anyhow. There's lots of different aspects of the PDB. And in 1989, there was a set of guidelines published about putting data in the PDB and what should be there. But again, it couldn't enforce it, except that the journals began to say, because of these guidelines, basically you can't publish unless you put your data in the PDB. Once the journals said that, that was it. And people started to put the data in the PDB, and the funding agencies, NIGMS in particular, said that if you do not have your data in the PDB, you can't have your grant. So there was only one person, one scientist who refused to put the data in, but everybody else complied. Okay, and so the PDB went along and it did fine. But people still were frustrated because it wasn't really very modern, and it wasn't really a dynamic enterprise the way it could have been. And so they put out a call for proposals. And even though I had been part of the B&L enterprise as a visitor, and I'd been very active, it was very clear that they just couldn't do what needed to happen. And so I competed against them, which was very painful. But we brought the PDB to Rutgers. We formed a consortium with SCSC and NIST. Again, that was really important. And we then began a huge growth in the PDB, which I'll tell you about a little bit. The other issue that was very important was the way in which the data were represented was based on the 80-column holograph cards, and that caused a lot of limitations, which I'll tell you about. And so we developed a new data representation called MMSIF, which later became PDBX MMSIF. And in 2021, the PDB turned 50, which was kind of amazing. The summary of how things are now is that there are over 230,000 structures. When we started, there were 7. The number of depositions per year last year was 19,000 in 2024. The data are very heavily curated and validated following community-based standards, which is, again, very important. It's open access. It is a single archive. The master archive is kept at Brookhaven, but it is mirrored internationally at EBI, in Japan, and in China. There are 6 billion coordinate files that were downloaded last year. There's usage of the PDB, and there are more than 400 biological databases that reuse the PDB data. The impact, one thing is that it was responsible for the invention of an entire new field, which is called structural bioinformatics. There are a huge number of knowledge bases that are based on subsets of the PDB data. Every drug company relies on the PDB data for drug discovery. Protein design, making new proteins that do new things, something invented by David Baker at the University of Washington. And of course, all the protein design depended very heavily on the PDB data. And then the amazing achievement of the group at DeepMind, which is a Google company. John Jumper especially did the protein structure prediction for the first time. So when we formed the PDB back in the day, we knew that sequence in some way gave the information for structure, but we had no idea how that happened, and there was no way to predict. We just knew that was true based on other experiments by, for example, Chris Amundsen at NIH, but we really did not know how that happened. When the group at DeepMind were able to successfully predict the structure, they didn't solve the protein folding problem, which is the way people talk about it. But we now know that if you put in a sequence into the what the program is called AlphaFold, you will get a pretty accurate structure. So that is huge achievement. And the training set that they used was 100,000 structures from the PDB. So what does the PDB teach us about organizing useful scientific data? How can we make the data usable? How are the data curated? What's so special? I was told repeatedly the PDB data is special, but what's special about it? And how are the data represented? I was also told by the DeepMind folks that that the representation was absolutely essential to their ability to do the protein prediction. What role does the scientific community play? It plays a huge role. And can we generalize to other scientific domains, whatever it is that we learned from the PDB? And hopefully, it took us 50 years to figure it out. Hopefully, what we learned will be done in a lot shorter time going forward. So curation and validation. The data are very, very carefully curated. The incoming data is checked for consistency. The sequence is carefully checked, and that's really important. There are various kinds, there's standardized nomenclature that is used. And then we have to ensure that the data matches information that are in other data resources. So all that happens during curation. Then there's validation, which is this data mean anything? Is it correct? So you can check the geometry of the protein by various methodologies that have been developed, and also the consistency of the model against the experimental data has to be checked. So I'm just going to give you just a quick overview of how that's done. So the data comes in. We now have a worldwide PDB, so it can come into Europe or Asia or America, and the workload is divided geographically. The annotation workflow consists of processing the small molecule ligands. There's a big emphasis on that because those ligands are related to drugs and drug discovery, and we have to make sure that the chemistry is correct, and that's actually quite difficult. And then there's sequence processing, because the sequence of the protein is really key to its structure, that we now know for sure, and we have to do various checks to make sure that happens. There's also sanity checks. There's some manual annotation, just look at the thing and see if it makes any sense. And then we have some various kinds of visualizations of how good or bad the validation is. And then the data are disseminated worldwide. So for the data checking, we have the ligand processing. This is just a graphic that shows you all the different things that we have to think about. And we had to come up with clear nomenclatures for the ligands and for the ligand geometry. And we check it against other ligands. Those ligands are small chemicals that are often attached to proteins. And so we have to check, did we ever see this before? Is this new? Does it make sense chemically? And then sequence processing, we check the data against sequence databases that already exist, like UniProt, which is at the EBI in Cambridge or in Hingston. And so we do all that checking, and that is done. We have lots of software to do it. And then, as I said, there's this sanity check. And I'll tell you a little bit about the people who do the sanity check soon. Validation in principle is the concept of establishing or checking the truth or accuracy of something. And so we spend a lot of effort on validation and making sure what we're handing out makes sense. So how do we figure out what to do? The PDB has some very, very good scientists on the staff, but they do not know everything. They have very strong backgrounds. But in order to do this right, we made a whole series of task forces for different things. So we have the first one was an X-ray validation task force, which has to do with X-ray crystallography and all the different things you have to worry about with respect to that kind of data. We had an NMR task force, Electron Microscopy task force, small angle scattering. We had a hybrid methods, which means using lots of different methods to calculate a structure. So we had a series of these task forces, and each task force would take 2 or 3 years to say, what are the standards for validating these data? And then publish a white paper, and then the PDB implements their recommendations. And this is ongoing. This is constantly happening. There's always new things, and there's always there is this process of having the experts look at things and then make recommendations, and then the PDB implements those recommendations. So this is just a graphic showing that was produced by the PDB for 5 easy steps for PDB deposition, with the tool that we use called OneDep, and tells people exactly what they have to do. And of course, we have real documentation that it's not in color, that people actually use. What about representation? The PDB format, as I told you, conformed to the original format to legacy punch card format. So that means that you only had so many columns for each of the things that are in a coordinate file, which includes, for example, the amino acid name, the number, and then the actual XYZ coordinates that are in the PDB. So that kind of thing presented all these limits. But people absolutely loved that format. And even though we knew it was all wrong in terms of modern science, it was very hard to actually get rid of the format, but we eventually did. So there's limitation on the number of residues. Large files had to be split, so there are now these gigantic molecules that have lots and lots of atoms, and the 80-column format wasn't going to allow that, and so we had to split. So that was all not good. And then there was extensive external format documentation that had to be read in order to know what you had. So this is not the way it should be. So again, community effort over many years, we created something called macromolecular crystallographic information file, because at the time we were only dealing with X-ray structures, and later when we started dealing with NMR structures and cryo-EM and now other things, we call it PDBX. There's absolutely no limitations on the size of the molecules. There are explicit relationships among all the data items, so there's nothing left to chance. Self-defining, so it's self-defining, so that means that when you read a PDB file, it tells you what you're about to see. It's designed as a series of tables, so it's easily loaded into a database, and then there's lots and lots of tools and libraries and documentation. So it's a kind of 3-layer system. There's a dictionary definition language, which tells you what's going to be in the dictionary. I mean, if you really want to get into this. And then there's the actual dictionary, which defines everything in detail, including the controlled vocabularies and all the relationships among the data items, as well as things like parent-child relationships, are all in the MMSIF. And then the data files themselves. So this kind of a setup means that An engineer can come in and handle the data without knowing anything about structural biology, which is really important. And that's one of the reasons that it has such extensive usage, and also why the DeepMind engineers were able to just take the data. When they tried to use PDB format, it didn't work. But when they used this format, it worked because it was all machine readable. And so they could actually know what they were getting at. Okay, so who does the work? First of all, who does the work are all the people who solve these structures all over the world. And there are, as I said, thousands and thousands of structures, and it involves teams of scientists. So that's the most important thing. The biocurators review the details of every structure, as I told you. Almost all have PhDs in structural biology. They're globally distributed around the world. There are regular meetings to discuss what's going on. So they have these summits, and they have them wherever they need to have them when they talk about what the issues are. The jobs post-PDB are in academia and industry, and we have a few people who have left, not that many leave, but the people who've left have become assistant professors, or they go to Google. It seems to be what happens. And they're very involved in outreach. They go to meetings and they talk to people and they bring back what they hear. So this is a picture taken pre-COVID when people were actually on site. And these are some of the annotation staff at Rutgers. The software developers create the tools for biocuration. So there's lots and lots of software for doing biocuration, for deposition and validation. The tasks are divided among the sites. And again, these guys have regular summits and meetings to talk about what they need to do. This was a summit that was held at EBI with the software people. There are external committees that provide advice and consultation, and the advisory committees provide high-level recommendations, and then the community task forces and working groups provide detailed recommendations for standards, and this is an ongoing activity. So you can tell I'm really into standards, and I'm kind of tougher than some of my colleagues here. And Carl has a story he could tell you about me as the standards person, but I'll kill him if he tells me. So the way I see it, to do this right, you have to have a continuing involvement of the science, the technology, and the community. All of that has to feed in to make a really good data resource. And so this is just showing over the years how all of that has changed. And this, just some pictures of all the people who've been involved over the years in trying to build this data resource. So in principle, I'm retired, but not quite. But I've gotten involved in a lot of things trying to understand what it is that I did over the years anyhow, because I didn't know what it was really. So I joined something called the Stakeholders Alliance, and began to work with this group. It's headed up by, he wouldn't like us to say it that way, but Joel Gershenfeld at Brandeis. And lots of people have participated, including some people in this room, where we kind of talk about how consortia work, how does collaboration work, and how does a consortia work. And somewhere about 15 years ago, I was told by library scientists that the way in which we were running the PDB conformed to Eleanor Ostrom's idea of where you have collective action from bottom up. So you have different people figuring out step by step what has to happen. And I didn't know that because I don't know anything about sociology. I'm now learning from Joel. And then there's other way, which is top down, where somebody says what has to happen. In my opinion, for this kind of project, it would never work. And it's not the way to do it. And then there's the thing that the Stakeholders Alliance has come up with, which is the idea of lateral alignment. And in lateral alignment, what you basically have is different groups of people who have different ideas about how to do things, but they have certain things in common and that they share with one another. And so there's the concept of both collaboration among these groups and competition. So the worldwide PDB, which is how the PDB is managed, consists of these now a very large number of groups. And the only thing we agree on for sure is that we're going to present the data the same. We're going to use the same tools for processing the data, and we're going to keep the data open. Those are the rules for the WWPDB. And we can compete with one another about how things are presented on a website and the services that we provide. So depending on where you go to get your PDB data, you will have all kinds of interesting services that come from, in America, it's the RCSB, in Europe, it's PDB-E, in Asia, it's PDB-J, and PDB-C is setting itself up. And so we believe in that, and in that way of working. I did not know that it followed the principles that have been laid out by the working group, the Stakeholder Alliance, but basically we're doing what's called lateral alignment. So I was glad to realize that there was actually some method behind what it is we're doing. So how can other groups follow the example? And what if they wanted to follow the example of PDB, how could they do it? One of the first things that has to happen is you have to figure out what problem do you really want to solve? Because the way in which you gather your data will depend on what problem you want to solve. And so again, after the fact, I realized that the decision by the PDB to include in the data set both the sequence and the structure in the same place, have those labels in, was key to the ultimate success of protein prediction. Reach out to others with similar interests. That's really fun and important, and you'll get new points of view, and you won't always agree, but it's really an important thing to do. And then what data are needed to solve the problem that you're trying to solve? And you have to think hard about that. And then, in my opinion, create a data dictionary of well-defined terms that's completely machine readable. And that's really important. And then you can create database. So from the PDB example, we feel that a data dictionary is absolutely essential, and that it has to define the terms, it has to give also the controlled vocabulary. And so if I were to have a slide that showed you all the people that have been involved, it would be thousands at this point. So instead, what I did is just tell you who's doing things now. We have the RCSB PDB, which was started by myself, Phil Bourne, and Gary Gilliland at NIST, and now is run by Stephen Gurley. PDB-E, and my colleagues who used to run it, and now it's being run by Samir. PDB-J is run now by Genji Kurisu. PDB-C is new, and so we haven't really had, it's brand new. So I'm not sure it's completely functional. It's partially functional, but we have PDB-C. And what's really interesting is that Genji's group trained the Chinese group in a very harmonious way, which was great, given some of the things that were going on at that time. And then the original BMRB is for NMR, which came in after the X-ray and was started by John Markley, and then Jeff Hope is in charge. And then we have EM, again, been a series of people running EM data, and right now being handled by Kyle Morris. We also have something that Carl's been involved with, and we used Emerita for, which is for the integrative structures. Those are the structures that come from multiple methods, and then using computational methods, you get a new model. And these are for gigantic molecular machines. And PDB began at Brookhaven. It was set up by Walter Hamilton. Unfortunately, he passed away the day we got our grant, like 2 years after this thing began. Walter died. And then Tom Ketzel took over, and then from him, Joel succeeded Tom, and then the whole American branch moved, and then we made ourselves global. And the funding, which we still have somehow, is from NIH, NSF, and DOE for the American. And it's been, again, a complicated way of doing the funding, but it worked. And then the groups in Europe and in Japan. So that's what I have to say.
And for those who are attending remotely, you can unmute and ask a question as well.
Helen, wonderful overview of math.
What?
Science. Partnership there.
Well, we have a formal training procedure, and we're constantly interacting with people in computer science and statistics when we get ourselves into trouble. But I'm not sure I fully understand your question. So,
I mean, the core expertise.
yeah, and yeah.
What I didn't. Partners as well.
Well, we have had collaborations with, for example, library science at Rutgers, and a lot of the people who come into the project have had training. And we've been involved, especially in the earlier days of the RCSB, in a lot of the activities with data and with, so we've done all that, but I'm not 100%, I mean, we're not working in isolation, if that's what you're asking, yeah.
We're all trying to find to build this workforce. There's a real gap.
Yeah.
We don't make.
So we want, so for example, we want all of our curators to also be, at least have some project having to do with software development. And if they can't do that, then there are other things that we haven't. We have one person who spends his time on statistics and has some background, and we encourage them to learn new things. So we don't want people to just be sitting in their cubbies and
Yes.
Like-minded people contributing and making process, because I imagine that.
yes, it was, and it was not done in a very formal way. I didn't, as I told you, I didn't know, I was involved in a lot of that part. Okay, I didn't really know what I was doing, but I would say, well, I think this guy knows this and this guy knows this. So let's bring them together and have a little get together. And that's the way we did it. It was very, very informal. When Stephen Burley took over, he made it much more corporate, so it was different than the way, but when I started, it was sort of almost like a mom and pop shop. Or it was a mom and pop shop.
Yes,
Yeah.
Passing forward, just looking at it. We need a database.
I have an answer about the standards that I can do, but go on.
Yeah.
Yes.
Very different from, let's say, FaceBase
Yes.
deal with. PDB. You have
Yeah, okay, so there's like two parts to the PDB. If you think about it, there's the data in part and curation and making sure the data is absolutely solid. And so our early focus was that. When it became possible to distribute data via the World Wide Web, okay, then we began thinking about these different kinds of services and what could we provide. And that's a sort of different part of what we do. So that part is much more like a knowledge base, okay, because you have all these things where we have connections with all these external databases and external resources. And so there is this kind of separate thing where you just focus, let's get the data right, and then let's see what we can do with it, okay?
scope creep.
Well, no,
Project like link out do something.
so that's what all these crazy meetings that we had,
Yeah.
it used to be pre-COVID, it was all, all in-person meetings and a lot of discussion and a lot of arguing. And then within the PDB itself, we had retreats where we actually said, okay, how far should we go? And we would spend 3 days, not just, we would like really have everybody involved, and they would argue and we would argue. You asked about standards, Rob. So one thing that is a little odd, in my opinion, is that the crystallographic community is very focused on standards and always has been, okay? So they're kind of very strict about standards. So we have something called the International Tables of Crystallography, which has exactly how you do your coordinate systems, how you represent symmetry, everything. So from day one, the crystallographers were into standards, which is a good thing because it would be almost impossible to imagine how you could solve a structure without those standards. So it was very standards oriented. So it's not unusual for this particular database to be so focused on standards. So we were inculcated on standards, and statistics. That was the other thing, is we had to know statistics really well in the early days. Now I don't think anybody knows anything, but back then they did.
Okay, great. Thank you so much, Helen.